So guys, if you're watching this, right now we're going to be talking about the quantum model of the atom. It's the model that came after Bohr's model. But it'd probably help to watch the previous video about chapter 15 before seeing this one, because it's kind of hard to understand unless you get the idea of wave-particle duality. So if we remember Bohr's model, that's where we have a nucleus, right, with its protons and neutrons in there, with electrons that have to exist at discrete levels, or in other words, specific distances, right? Now, Bohr, as well as Rutherford, they both had this problem, and they knew it, but they just kind of came up with a model still saying, beats me, I don't know how to explain how electrons are really orbiting around the nucleus. So what happens if you have an electron, right? He's negative. If you have a nucleus, that's going to be positive because of all the protons. The neutrons don't really have an effect as far as charge goes. So the electron, it wants to be pulled into the nucleus, kind of like the moon wants to be pulled into the Earth, right? So we learned about that in chapter 4. The thing is, how do we keep that electron outside of the nucleus? Because we know the electrons aren't supposed to be in there. They exist on the outside of the nucleus. So what Rutherford kind of figured out, even though he saw a problem with it, was that the electrons were orbiting, or in other words, going around in circles, being pulled in because of electromagnetism, kind of like the moon is pulled towards Earth, except for that's with gravity. Now the problem with it is that the electron is accelerating. Now it might be kind of hard to see at first what the issue is with that, but whenever we have an electron that's accelerating, or changing its motion, it needs to be radiating energy. So you don't really have to understand exactly why, but whenever you have a net force, you have an acceleration, and you need an energy to be associated with that. Now, whenever you have an electron that's accelerating, it's going to be radiating energy. And if it's doing that, we already learned in the last model that it's going to be spitting out different colors of photons. So if we have an electron that's orbiting around a nucleus, it's accelerating constantly because it's not traveling in a straight line. It's going around in a circle, constantly changing its motion. If it's doing that, it should be radiating energy. And if it's doing that, it should be spitting out photons and eventually getting closer and closer to the nucleus until it crashes in the nucleus. So really, atoms with this model shouldn't exist for more than a couple of nanoseconds. But we know that doesn't happen because we're made of atoms and I'm still here. So electrons, they're not supposed to be accelerating. That's something that they just didn't really know how to explain. Now, whenever we think about the quantum model, or whenever we think about quantum physics or the duality of matter, it might help in this situation to think about electrons more as waves instead of particles. Because I can't come up with a way that a particle with a negative charge can exist outside of a positively charged nucleus without accelerating. All we know is that it exists outside of the nucleus, but it's not supposed to be accelerating. So let's think about this. There's a lab that I'm pretty sure you guys have done from the beginning of this unit where you're playing with waves. So say you have two people that are holding a jump rope, right? If one person plucks one end of the jump rope, you see energy that's kind of being radiated towards the other person. So yeah, that's energy being radiated. But what if instead of plucking it, you start spinning it like this? What you get is a standing wave. Whenever you do that, energy is not being radiated from point A to point B. Energy is actually just kind of trapped right here in what we call the antinode. Now, if you wave it a little bit faster, you see these different shapes that kind of happen, right? So this is still a standing wave, just of a higher energy. Now, whenever you have that, energy is not being radiated from point A to point B, it's just being trapped right here in the antinodes. Now what that means is that you can have energy that exists without necessarily accelerating or without being radiated. Now we can forget the jump ropes for a second, let's talk about electrons. If electrons are waves instead of particles, the same thing applies. You can have energy that exists in standing wave patterns without being radiated, the same way like the energy in the jump rope goes. So electrons, we could honestly stop thinking about them as little points or little particles. We could think about them just as waves or clouds of negative charge. If we do that, then say we have a nucleus like this, right? Then maybe the electron is actually just kind of a cloud of negative charge existing as a standing wave outside of the nucleus. This is one way to interpret it. So this, forgive my bad drawing, this is supposed to be like a three-dimensional sphere. It's an image of what the electron is actually supposed to look like. Now, if we decide to observe it, if we decide to, poke at the atom, we can insist that the electron behaves as a particle, and, that particle is probably going to exist somewhere within the sphere. If we're not observing it, if we're just letting the electron do its thing, it's going to be a wave. So this is honestly what electrons look like. It's not like the electron is necessarily somewhere inside of this ball. The whole thing is the electron. So if we understand that, the electrons are actually just standing waves, then it starts to make more sense. It kind of solves the problem with Bohr's model. So these electrons, they have energy, just like the jump rope, that exist in antinodes. They exist in, wave patterns, and they're not being radiated. Now, if electrons have higher energies, they're going to take on different shapes, and they start looking kind of funny. So they'll take on this shape as well. This is what we call a p orbital. And again, these are just three-dimensional shapes, pictures of what waves would look like. And this even kind of looks like what the jump rope looks like whenever you have people standing on either end doing this. Now, I can't exactly give a model with a jump rope for further pictures, but electrons, they're not strings, they're different. So they come up with different shapes. This is one of the d orbitals. It looks like two p orbitals that are just kind of sideways, or in other words, like a four-leaf clover. Another d orbital is this one. Looks like a dumbbell and a donut. Just remember that, dumbbell, donut, d. So this is a d orbital. And then you have the f orbital as well. So let me label these real quick for you. This is the s orbital, this is the p orbital, this is the d, this is another d, and this is the f. So it'd be good to memorize these shapes. Even though I kind of got lazy with these pictures over here, these are still three-dimensional images of waves or of clouds of negative charge. So that's what the electrons look like whenever they're around an atom in different energy levels. So that conceptually is kind of why it solves the Bohr model problem. I mean, it adopts everything that he talked about except for the fact that electrons are orbiting. So instead of calling these orbits like this, where they go around in a circle, they call them orbitals. Or in other words, waves, three-dimensional waves that exist around the nucleus. So that's kind of the basis of the quantum model. This is kind of Bohr's model where we have our electrons measured on these little rings, where we know each ring represents a different shell. Instead, we represent them like this. It's like a tub where you have your shells measured in different depths. So this down here we'll call shell 1. This right here we'll call shell 2. And this right here is shell 3. Okay? So if you're looking at the periodic table, you can actually divide this up into different groups according to these shapes. Now for this example, we're going to go ahead and put helium over here in the S section. When I say S section, we're going to divide the periodic table up into these groups. Okay? So over here, this is S, this is D, this is P, and this is F. And whenever you're in those sections, the electron that corresponds with that section is actually going to look like these shapes that we just talked about. So whenever we talk about shells, that's going to correspond to different rows on the periodic table. If you go down 2 rows, let's say you start on the first, you go down 1 and down another, you're going to be in shell 3. In order to fill up these energy wells, you have to see what section you're in and what row you're on, and you have to read through the periodic table like it's a book until you get to the element that you're trying to fill up for. So let's say this one is like lithium. So for lithium, we know that one's right here. If this is hydrogen and helium, this one would be lithium right here. So we start off up here with the number 1. Now this is in the S section. So this atom would actually have one s orbital so far for that electron. Whenever we move over, reading it like a book, we see helium. That's the second electron. That's going to be housed in the same orbital, just with an opposite spin. We represent those with different arrows. So s orbitals, those can hold 2 electrons. One with an up spin, one with a down spin. Now after we do that, notice there's nothing else on that row. So there's nothing else in that shell. Whenever we come down again, we're going to see lithium right here in the second row, but still in the s orbital, or the s section of the periodic table. So what happens is you're going to have another electron that's in the next shell, but still in the s orbital. Now we represent s orbitals just as flat platforms in this picture. And s orbitals, they can only hold 2, so it's just going to be one flat platform. P orbitals, they can hold 6 electrons. So you're going to have it as 3 platforms, each platform holding 2. And as far as D and F go, you have to know that these shapes exist, know what those shapes are, know what they look like, be able to label them. You don't have to worry about them whenever we're filling energy wells though. So for p orbitals, just remember that's going to be 3 platforms housing 6 electrons. So this is what we would fill up for lithium. If we wanted to do another element, like let's say sodium, we know sodium's got 11 electrons, right? So reading the periodic table as if it were a book, filling sodium up, we start with hydrogen again. We know hydrogen's electron is going to be right here in the s orbital in the first shell because it's the first row and it's in the s section. Helium, that's also in the s section. So we give that electron to it. We go over to the next element, which is lithium. For lithium, we give him his electron. He's still in the S section. Same thing with beryllium. Now after beryllium, and I didn't draw this perfect, let me fix that real quick. So this is hydrogen, this is helium, this is lithium, this is beryllium. After that, you go over here and you skip the D section and you go straight into the P section. In the P section, you're gonna start filling that one up. So you draw those platforms and you start here, right here with boron. And you give them that electron. And you keep going through the elements, filling up the energy well, like so. And then by the time you reach the end of that row, you'll be a neon, which should have 10 electrons. You'll have filled that P section. So after that, you have to jump down a row, just like a book, and you go over to the next element. That's in the S section. So since you jump down a row, you jump up a shell. And since you're in the very first spot, it's in the S section, give it an S platform. And then you're at sodium, which has 11. You give it its 11th electron. So that's how you fill these things up. Now, it might be a good idea to go through a couple of examples. Just give yourself a random element. Just don't go past argon. So any of the first 18 elements, and try to fill up its energy well. And it might help to be able to look at the periodic table, try reading it like a book, try seeing what section you go through as you read it, so you know exactly what platform to put in this energy well diagram. And that's how you're going to be able to fill it up.